All right, I believe it's working. Thank you to everybody for being here. I just have to say, I'm very happy to have family on both sides of the aisle here. We have, I came from Michele and Marek working on detection and a lot of more parameter estimation side, but I've recently moved to, well, I guess not that recently anymore, Tony's group and working with Håkan Andresen on more of the simulation side. So I'm very, very happy to see everybody at this meeting. That's kind of what I wanted to talk about with this talk. We're going to talk about low-frequency gravitational waves. I know pretty much everybody is only ever worried about the high-frequency gravitational waves, and I mostly agree with you, but I do think there's a lot of promising science that we can approach within low frequency. And again, you know, both sides of the family, theory and detection, we're going to talk a little bit about both of those. I will also preface the QR code. It's going to come up again. We have our gravitational wave data from our neutrino strain and our matter strain from the recent D series that Daniel talked about. That's all online now. You can just go to that website and download it. But again, I will talk about it in a couple minutes as well. So a brief review of what we're going to talk about. I'm going to talk about core collapse supernova gravitational waves, not that we all haven't heard about that already. And then I'm going to go directly into the low frequency portion of those gravitational waves, where I'm going to motivate some match filtering for detection and parameter estimation. All right, this is a slide that we've mostly seen before. So I'm going to move on from pretty much all of it, but I'm going to focus on this small black square where we investigate the low frequency memory of these gravitational waves. So there we go. As Bernard mentioned earlier, we do look at two sources for low frequency gravitational waves. We have the large scale matter motions and the anisotropies that are prevalent in the neutrino emission. So I'm going to play these two movies at approximately the same time, give you some time to look at them. I do apologize, they're not time synced, but they're going to get the main idea across. The black rectangle is going to be our hydrodynamics, and this red circle is going to be our neutrino luminosities. So early onset for both of these, we can wind up seeing a lot of the convection start in the matter portion. We see the neutronization burst as the electrons and protons combine in the collapse phase. And then eventually, in the matter portion, we start to see these large-scale asymmetries develop. This is the D15 model that Daniel was talking about earlier. So we start to see very large kind of oblate and prolate motions. And on the neutrino side, we can see this kind of bubbling. We see these hot and cold regions right next to each other. These are the asymmetries that lead to neutrino gravitational waves. In the hope of time, I'm going to move past these and move on to the gravitational waves from the neutrino anisotropy. As Bernard mentioned earlier, and as Tomas mentioned for the white dwarf scenario, we can get gravitational waves from neutrino signatures as long as we have the directional luminosities of the different neutrinos and the different neutrino species. So following what was done all the way in 1978 and then followed up by the Garkin group, we calculate the anisotropy, or how non-spherical the neutrino fields are from the luminosities. And we do it for all four of the species that are evolved in Chimera. And then using that anisotropy and the total luminosities, we wind up calculating the gravitational wave emission as well. And the thing to note is it is very low frequency. We do see some high frequency evidence, but it is nowhere near the scale of anything else that we're going to talk about. We do evolve four species of neutrinos, and we have to take into account the anisotropy of the entire field. So that's why we have this total gravitational wave from neutrino signature there as well. Here's another example of some of our gravitational waves from just the neutrinos at different viewing angles for the 25, 15, and 9.6 solar mass models. But coming from both sides of the family, we like to look at spectrograms. This is from the 9.6 model, where the black curve is going to be the total expected gravitational wave signature, made up from the blue and the green lines. The green line is the neutrino signature. The blue line is the fluid flow signature only. And in this case, we see the signals adding constructively. The total signal is a larger amplitude across the board, but we can have another situation for this, the D15 model, where the neutrinos and the matter are slightly opposing, so you wind up getting a more neutral current, a more neutral amplitude signal. And then finally, we have the case in this 25 solar mass model where the amplitude from the neutrinos is essentially non-existent, so the matter and the total signature are not very far off from one another. But regardless, the neutrino signature is going to impact the total strain. And I think this is something that we as a community should look into a little bit more, because we're not looking at the right signatures. There are gravitational wave sources across the board that we need to start implementing more in our detection pipelines, and on the simulation side, looking at what's coming out of them. So a lot of this motivates some of the previous work that we just did, 2024, where we investigated matched filtering. So here we have that same spectrogram from the D15 model, where we have, just as we've talked about previously today, that high frequency feature. We have evidence of the SASE, and then very, very far down here, we have this bright red bar, which is indicating the memory. Now, the key point is the spectrogram shows evidence that is a non-zero frequency for the memory. Now, it's not exactly the memory, it's the ramp up to the memory. And I'm sure a lot of people, at least on the LIGO side, have heard me talk about this before. But this is what we want to investigate, this ramp up to the memory. Now, it is low frequency. Technically, the memory itself is 0 hertz. But this evidence, this ramp up, can lie anywhere between 30 and 50 hertz, which is definitely within current LIGO detection ranges. So we seek to investigate the memory, and we chose to use match filtering because that is a very straightforward way to start looking at it. But in order to use match filtering, we need to have a template first. So we have proposed this logistic template, or for machine learning people, a sigmoid function. But it can be characterized by 3 parameters. One of them is the final amplitude of the signature itself. One of them is going to be the ramp-up frequency, how long it takes to go from something 0 to non-zero, and then the central time of the ramp-up. But for our work, we can ignore the central time of the ramp-up because any injection software is going to move it around as is, and we can just shift the template as needed. So this opens us up to looking at each of the parameters for our function across all of the observer angles for our 3 models. So we fit the template to signatures from each of the models. That's going to be the different rows here, 9.6, 15, and 25. The left side here is going to be the frequency, the ramp-up frequency. The right side here is going to be the amplitude, the final amplitude of that function. And we look at it from multiple observer angles. So with this, we do a decomposition in phi and theta of 5 degrees. So we have quite a few signatures that we can investigate. And again, all of this data is available now for anybody to dig up. And one thing to note is when it comes to this template, the amplitude of the signature doesn't seem to have very many correlations, because like I showed earlier, there were some cases where the neutrino and the fluid signatures were both the same way, different directions, or just neutral to each other. But the frequency content matches that of the neutrinos. So the black curve in the back is the fitted parameter for the total function. The blue curve is the fitted function for just that of the fluid, and the orange curve here is the fitted function for just the neutrino signatures. And the black curve, the black histogram, lines up very well with the orange histogram in all of the cases, where the blue curve, while it may be tighter, doesn't have as much impact on the total signature. So now that we have a template, now that we have a parameter range to start investigating, we can actually start looking at match filtering as a detection prospect and eventually a parameter estimation project. And I'm going to briefly mention this. We start our investigation with a linear predictive filter. So for all of the non-detection people in here, we fit a function to real LIGO noise, and we essentially subtract that function from the noise. It is a lot more complicated than that, and I think Michele is going to talk about it more tomorrow. But one of the key features of this initial technique is we can decrease the amplitude of the 10 Hz wall here. Now, We're not looking at exactly the same data. That's why here we have the amplitude spectral density and this ASD hat. But when we apply the same template to the signatures, the gravitational wave signatures, the total signatures, we see that the noise is much more impacted than all of our signals. So we can use this linear predictive filter in time with the match filtering to get better detection prospects. And then we also fit different amounts of data that we train for the linear predictive filter and see that it does converge for larger training times. And so this is going to be the basic flow of our detection pipeline that people have seen before. We start with real LIGO noise from the Gravitational Wave Open Science Center. We train a linear predictive filter on that signal without the data. And then we start with our signal. We do some fitting and extension techniques that I'm not going into too much detail in the advent of time here. But then we apply a tapering to remove a lot of the high frequency artifacts that you get when you have a non-zero signal going to a zero signal. And then we take that signal, we apply it into the gravitational wave noise. We take this new noise plus signal, apply the linear predictive filter, and then subtract that predicted data. And then from our signal, we have a template or a bank of templates in which we're going to investigate, and then we wind up getting correlations. And the correlations are what's shown up here, where, at least in this study, for this chunk of time, we were able to clearly identify the 25 solar mass model, the 15 solar mass model, mostly well-defined, and the 9.6, we just had an unlucky spat of noise there. But if we look at the false alarm probabilities down below, we can wind up seeing that for relatively normal signals, 10 kiloparsecs, that's a standard that we're all used to hearing at this point, we can wind up getting fairly good false alarm probabilities for the 15 and the 25 solar mass progenitors that we studied, but the 9.6 kind of needs more investigation, which we are currently doing. All right. So in conclusion, I do want to, one, motivate. We should be looking at the gravitational wave signatures from these different sources, from fluids, from neutrinos, and for those who have MHD capabilities, from the actual electromagnetic fields themselves, because they are all going to contribute to the total signature. And this study that we originally published was a very short study because we wanted to get the community involved to actually look at this, because our signatures are relatively low in amplitude. As we saw, we go from about 15 to 20 centimeters at the source for the 15 and 25 solar mass models. But as we've seen today, stuff that Tomas talked about, 20,000 centimeters for a white 20,000 centimeters for a white dwarf, and the study led by David and the Princeton group, we have a lot of room to detect these very high amplitude signatures with this methodology. So again, I just want to emphasize, we do have our data here available now. Anybody can download it. I have a link because this is also uploaded on Indico. But low frequency gravitational waves are detectable in current detectors using this linear predictive filtering and this match filtering. We have seen studies show the low frequency signals need to be included in any of these detection techniques. And again, that last bullet, just want to point out, all of the Chimera data for the D series is available at that link as well. A couple references, and I believe I'm 1 minute under.
Perfect.
Thank you.
So thank you very much. We've got time for your questions. Stop.
So we know the gravitational wave signal is below 10 hertz, right? But we're making the spectrograms and whatever, and we still see it like leaking into the LIGO band. But how can you be sure that this is something that LIGO's definitely going to see, and that it's not just like spectral leakage from the way we're doing the windowing and the Fourier transforms and stuff of the gravitational wave signal?
So 2 points to that. One, the memory itself is 0 hertz, exactly like you said. It is the permanent deformation. But as this signal shows, I love this plot because it shows it very well. When you have completed explosions, you go from a non-zero to a zero, or a non-zero, zero amplitude to a non-zero amplitude in a amount of time. And that amount of time, which we call the ramp-up frequency, is above the 10 hertz wall. So while we're not directly detecting the memory, we are detecting evidence of the memory the best that we can. In future detectors, so any of the lunar detectors or LISA, we're still going to face this problem. We'll never be able to actually detect the memory. And on top of that, I mean, this shows that using real LIGO data and our flow chart here, we can make detections out to 10 kiloparsecs using this match filtering technique. I hope that answered all of them.
I can add comment up if you want to.
So I think I have just a quick question. How does this picture change with either Cosmic Explorer or Einstein telescope? It seems like that should open up windows for us. Is that true?
So I'm going to be selfish right now and just say that what we got for 10 kiloparsecs is shown here, fairly good detectability. With Cosmic Explorer and Einstein telescope, we're going to get an overall amplitude decrease of about 10% on the noise curve, and that 10 hertz wall is going to move about 10 hertz back to about 1 hertz. So we would expect upwards of, I don't want to say expect, but we would hope for 100 times further distances. And so with this technique, we can push into the large and small Magellanic Clouds, which would have given us 87A. But I'm younger than that by a lot, so. I wasn't going to go that far. I'm being conservative right now. There's a lot of detection people that might want to eat me up here.
I was wondering, why do you do linear predictive filtering if you're doing match filtering? You don't need that.
So the investigation of the linear predictive filtering, and I don't want to take up too much time, so I'll leave that to Michele to talk about more tomorrow. It really was just to give us another step up. The linear predictive filtering was meant to only work on the noise. And obviously, we apply it after we inject the signal, so the filter affects the entire data set that we're looking at. But it was trying to pick out more of this part of the signal between 20 and 40 hertz where we see evidence of this memory ramp up.
Okay.
So we found that in the first, going from the first half a second out to several seconds, the neutrino strain contribution really ramps up, reaching hundreds, in some cases 1,000 HD centimeters. And so that could, for Einstein telescope or DESCO, really expand the detection horizon for non-rotating jet-lit supernovae out to hundreds of kiloparsecs,
Yes.
megaparsecs.
Yes.
How would that affect your false alarm probability for some models?
I don't want to speak to that because we would have to actually inject those signals and see. I would be hopeful in that, since the gravitational wave strain goes as the amplitude, we would see larger signals either from closer supernova, or we would see further supernova with amplitudes relatively what we expect for a galactic case. So hoping that we would see it further is the big thing.
Hello. Do I understand well that the detection statement that you're making later on is based on an hour of LIGO data?
Yes. One more. For this investigation, we only investigated one chunk of the LIGO data from GWASC, which is 4896 seconds, because we wanted to try and do as much as we can with as little data as we can. We're currently working on something that has longer times and more of the LIGO data analysis techniques that people are used to.
So statistically saying, this means that you can only constrain to false alarms in 1 per hour, right?
Yes, for right now. And I think Michele will probably talk more about all of the constraints from the data side. I had a short talk, so I had to keep it limited.
Give an answer to everybody, but I don't think you're that fast. People can come and talk to me after the talk if they want to, and I'll be happy to talk in the corridor.
besides this, any other comments, questions? It's not to be the case, then let's conclude this part of the session by thanking Colter and all the other speakers.